Great. Okay, so before I go on to my talk, I need to wear my hat as an organizer and tell you guys that there's the lunch is organized at the physics auditorium. Okay, so you should head there for that.
But now he's a speaker. and he was already Suvrat was already acausally introduced by the previous speaker. Okay. So he will tell us why there's no firewalls.
Okay, so thank you to the academic organizers of this session for asking me to speak here. I should say before I start that what I'm going to talk about is almost entirely based on work with Kyriakos Papadimos. We have a number of papers in this. I'm going to talk about our most recent 2 papers and also some work in progress with Shouvik Banerjee, who's a postdoc at Groningen, Prashant Samantare, who is a postdoc at ICTS and is now at IIT Indore, and Sudeep Ghosh, who is a student here at ICTS. Even though the title of my talk is about the reconstruction of the black hole interior, really the context for this talk is the information paradox. And the relation between these two is that when you think of the information paradox, as I'll try and describe to you in its modern avatar, it turns in a sense into the following question. It turns into the question of, can ADS-CFT describe the interior of the black hole? And that's the relation between the title of my talk and the information paradox. And as I'll try and emphasize to you, this version of the information paradox is not restricted to evaporating black holes, which is where we usually think of information loss, but applies also to the eternal black hole, as we showed earlier this year and as I'll try and review. The main thing I want to emphasize in this talk is I want to present a resolution of this paradox in terms of what's called a state-dependent map between the bulk and the boundary, which you already heard about briefly in the previous talk. And I want to talk a little bit about new consequences of this construction and point out that it's not only good for resolving these paradoxes, but also leads to a natural setting for what's called the ER equals EPR conjecture that some of you have heard about. Okay. This is an overview of my talk. Before I go on and talk about the modern information paradox, which is the recent avatar I talked about, I want to talk briefly about the old information paradox, and then I'll review its version for the eternal black hole and its resolution and the application to ER equals CPR. So let's first talk about the old information paradox, which is how you would have heard of it. Old means up old, few years old. And so the old information paradox goes as follows. Imagine that you're living in ADS-CFT and you turn on a source at some point which creates a shell that collapses into a black hole. This is the horizon of the black hole, and then you're interested in physics in this blue patch up near the top. So Hawking showed, and you can easily generalize Hawking's calculation to ADS, that physics in this blue patch on top, which is far after the shell has gone through, becomes universal. And in particular, if you quantize the field in terms of Schwarzschild modes, then the 2-point functions of these modes and also higher point functions look like they're modes in a thermal ensemble. So you can compute some 2-point functions. And if you take this seriously, this suggests that for different inputs, whatever form the shell, you get the same output. So you could start with input A, and the black hole would convert this into black body radiation, and you could start with input B, and the black hole would still convert this into black body radiation. And if this was true, it would be a clear violation of unitarity, which tells you that physics has to be reversible. But really, this is not so much of a paradox when it's stated in this way, and the reason it's not so much of a paradox is that it's been well understood for some time that very small corrections of the order of e to the minus s can unitorize Hawking radiation. And one way to say that is that if you can easily think of density matrices in large systems which mimic a thermal density matrix to excellent approximation. So you can think of a pure density matrix in a big enough system that looks exactly like a thermal density matrix up to terms of order e to the minus s by 2. And another way to say it is that you could take the thermal density matrix as computed by Hawking, and you could add some very small corrections which are of size e to the minus s in this way of measuring things, and you could get a pure density matrix. And there's a slogan that goes along with this. And the slogan that goes along with this is that tiny correlations between the different Hawking quanta can encode information and restore unitarity, and these are the equations that go along with this slogan. Now, one question that's sometimes asked is, okay, that's very good, but where is the mistake in Hawking's computation? In fact, that's not such a good question either, and the reason for that is that effective field theory doesn't really have much to say about these e to the minus s corrections. And that's most clear when you think of quantum gravity as formulated via a path integral. So if you formulate quantum gravity via path integral, you're working about some saddle point, which is your classical black hole solution, and perturbative effective field theory is an asymptotic series expansion about this saddle point, but it has very little to say. It breaks down completely when you start thinking about the presence of other saddles, which would contribute at order e to the minus s. And there your notions of locality break down, because 2 points that are close by in one saddle point may not be close by in another saddle point, and therefore effective field theory can't really say much. And if there is some other argument that tells us that these corrections are required for unitarity, effective field theory can't really rule them out. And so there's no point in asking about what's the mistake in Hawking's computation. Small corrections in this version of the information paradox can restore unitarity. Okay, but that's not the end of the story, otherwise I wouldn't be giving this talk. Recent developments, starting about 5 or 6 years ago, and mostly with the work of Samir Mathur and then followed by the work of the AMPS collaboration, have challenged this notion that small corrections can fix the information paradox. And I'm going to review an extension of these arguments to the eternal black hole. And now the reason, the motivation for studying the eternal black hole is that we believe we understand the eternal black hole fairly well, and therefore any resolution that we propose, if it works in the case of the eternal black hole, provides strong justification for using a similar resolution in the one-sided case. So that's the reason for focusing on the eternal black hole, which I'll try and do for a large part of this talk. Okay, so let me just remind you quickly about the eternal black hole. The eternal black hole is this black hole which looks like a Schwarzschild black hole, a large ADS Schwarzschild black hole from one side, but it has two ADS boundaries because you do the Kruskal completion, and it's believed that this eternal black hole is dual to what's called the thermofield double state in two CFTs. So this is a state which consists of two entangled but non-interacting CFTs, which are entangled in a particular way with these thermal coefficients, and the claim is that this geometry is dual to this entangled state. Now there's just one point I want to make about this geometry, which is not always appreciated, which is that there are 3 times here. There's a time on the right, there's a time on the left, and there's a killing time in the geometry. And on the left, when you write down this identification, you identify the killing or the Schwarzschild or the bulk time with minus of the left time, but just with the right CFT time. Okay, so this is something to keep in mind. Okay. Now, before I go on to the information paradox, I need to introduce a slight generalization of this duality, and I'm going to do that by considering a slightly broader class of states, which are these states which are obtained by taking the thermofield double state and by evolving it, but evolving it only with the left Hamiltonian. So this is something that's perfectly legal to do in the CFT. You can see that it gives you these phases phi phi, which is just ET mod 2 pi. And you might worry about what this does in the bulk, but in fact we have understood for a long time that Hamiltonian evolution has a particularly simple interpretation in the bulk, and the particularly simple interpretation is that Hamiltonian evolution acts like a large diffeomorphism that doesn't die off at the boundary. So in particular, evolution by the left Hamiltonian corresponds to a diffeomorphism that dies off at the right boundary, but not at the left boundary. And it's easy to think of explicit examples of such diffeomorphisms. This is an example in these u and v Kruskal coordinates, and it's very easy to think of other examples that basically take a nice slice that's anchored at some point here on the left and some point on the right, and they push it up to this kind of a nice slice. So it's easy to think of such examples. But the point is that any such diffeomorphism is not unique. And the reason it's not unique is that you have to mod out by trivial diffeomorphisms, which are those diffeomorphisms that die off at both boundaries. So you can use this freedom to undo this diffeomorphism everywhere except for a region that's infinitesimally close to the boundary. And what this makes clear is that all this diffeomorphism is doing is sliding the boundary but leaving the rest of the geometry totally invariant. And therefore, it's very clear from this argument that these states psi of t, which are evolved by the left Hamiltonian, are also smooth black hole solutions, in fact the same solution, but glued differently to the boundary where you identify the Schwarzschild time with the left CFT time plus a shift. So this is a message which is totally independent of the information paradox, which is one of the messages I would like you to leave this talk with. Now I want to point out, I want to make a claim that this geometry is in fact smooth not only for small shifts but even for large shifts that are exponentially large. And you might worry about this, but in fact this is rather robust, and the reason it's robust is that in making this claim that the diffeomorphism left the geometry invariant, I didn't use the equations of motion, I only used the equivalence of Hamiltonian translations with diffeomorphisms, and that's something that you would believe should be exact. But in any case, there are other ways to understand this. By using the isometry of the thermofield double, this is equivalent to the statement that a right infalling observer sees a smooth horizon whenever she jumps in. And it's also in fact equivalent to the statement that there is no natural common origin of time in the two CFTs. So when you chose the thermofield double state initially, you chose a particular phase, and that phase had to do with choosing some arbitrary common origin of time, and so exponentially long means exponentially long with respect to arbitrary origin, and so it doesn't really mean anything. Okay. Now the other thing I want to point out, which was also alluded to in the last talk before I come to the information paradox, which is that the presence of the ADS boundary in fact allows you to get rid of this problem that you can't define local observables, and you can define quasi-local observables, and the particular observables I'll talk about are observables that are defined relationally with respect to the right boundary, which means I jump in from the right boundary, I wait for some proper time, and then I measure the field. And you can take this field as defined in this way and expand it in terms of modes behind the horizon, left and right moving modes, and the modes I'm going to be interested in are these right moving modes, which are the cause of all the problem. Okay, so I have enough now to frame the information paradox, and the information paradox is the following statement. If we really believe in the ADS-CFT duality, then there should be some operators in the CFT that give you the correlators that bulk effective field theory predicts about the eternal black hole background. So the question is, can you find some CFT operator phi of x so that its correlation functions computed in this set of time shifted states match the semi-classical Green's functions that you would get by quantizing fields perturbatively about the eternal black hole. Now sometimes people say that the discussions in this area are wordy, but in fact this is a completely precise question. It's a question, very well posed question about the existence of certain operators in the CFT, and a question of whether you can find this or not. Okay, so I don't have time to go through the proof. I'm happy to do it later in the discussion if you like, but in fact by extending the work of AMS, you can show that there is no such operator in the CFT that has the property that its correlators in all of these states equal these semi-classical Green's functions, and roughly the reason is that these states psi of t are overcomplete, and therefore by trying to specify the correlators of this phi in all of these psi t states, you overspecify the field phi, and you don't find a solution to that equation of motion. Now this looks different from the information paradox, but at the heart of it, it's still a conflict between unitarity and effective field theory, which is what the information paradox was as well. Okay, so now what are the possibilities that you have? Now one of the possibilities is that ADS is not equal to CFT. The duality between the eternal black hole and the thermofield double is just wrong, and this is something that was proposed in this paper by Marolf and Wall. And they proposed adding additional degrees of freedom so that you could describe the eternal black hole. They said you need to add these additional degrees of freedom in order to correctly describe the eternal black hole, and these go by the name of superselection sectors. You could say that the eternal black hole has firewalls living behind the horizon, and therefore there's no point in talking about these interior operators, or maybe what your semi-classical Green's function calculation is not valid because it doesn't account for these firewalls. But both of these possibilities are in the unpleasant situation of contradicting some explicit calculations you can do in the CFT, such as these calculations of Hartmann and Maldacena of entanglement entropy on the two sides, or correlation functions, which was done even earlier, that look inside this horizon of the eternal black hole and appear to see a smooth geometry. Okay. So that's not a good resolution, and I'm going to try and describe a different resolution, which is that you shouldn't try and use the same operator phi for all t, but rather you should use one operator phi around this thermofield double, and once you shift by an exponentially long time, you need to use a different operator. Okay? And that's what's called state dependence, that you shouldn't try and describe this observable by the same operator. So let me try and describe that more systematically. So let's say you start with one of these psi t states, one of these time shifted states. The first limitation you need to recognize, which was discussed in the previous talk, is that you need to realize that in effective field theory you can only measure some subset of excitations about the state. You don't really have access to the full Hilbert space, and in particular you can measure some single trace operators and some products of single trace operators, while you keep the frequency of each of these guys much smaller than the central charge, and the product of these guys much smaller than the central charge. Just to return the compliment, I should say that the paradox of the previous talk is completely resolved if you realize the same limitation about the ADS-CFT vacuum rather than one of these excited states. Okay, so in this state at psi, you can in this Hilbert space at psi, you can define this mirror operator precisely, and the way it's defined is by making link to something that's called the Tomita-Takesaki theory of modular isomorphisms, And so what you do is you take one of these product of single trace operators and you write down this S map that takes a state which is A alpha acting on psi. It's an antilinear map to A alpha adjoint acting on psi. And then you can define these mirror operators in some concrete way just in terms of S, and I can tell you more about how to pick this delta, but it's there's some precise prescription for how to pick this delta, and you can define these mirror operators. And these mirror operators, as I said, work about this little Hilbert space and not about the, you know, not in the full Hilbert space of the CFT. So in particular, in the eternal black hole, you can carry out this program very explicitly, and you get some explicit answer for these mirror operators, which is in terms of the left, you know, the modes of the left operators multiplied with certain projectors, and then you can smear these with some appropriate mode functions, which gives you some operator in the CFT, and then you can compute the correlation functions of this operator about all of these time shifted states, and it gives you the semi-classical Green's functions that you expected. Okay. And this construction, I have to say, explicitly resolves the information paradox, and the way this problem of over-completeness is avoided is because you're willing to shift operators once you shift the state by you know, this state t by a large amount, and that gives you more freedom. Okay. So let me describe now how this construction is useful not only for resolving this paradox, but also for discussing you know, as a natural setting to understand this link between entanglement and wormholes that was originally proposed by Maldacena and Susskind. So I have to first generalize this construction I mentioned, which I provided for the eternal black hole, to more general entangled systems. And so you can consider some general entangled state of the CFT with some other system, and then you have to realize that now the set of simple operators you can act with are simple operators in the CFT itself and some simple operators that may act in the left system. And therefore, this little Hilbert space that I define is now given by the action of this product algebra, not just the algebra of simple operators in the CFT acting on this entangled state. Okay. Now, you could have asked why I didn't worry about this in the eternal black hole, which was also entangled, and the reason for that was that the action of a left operator there can be represented as the action of an ordinary single trace operator. In general, you won't have so many null relations, and what will happen is that this action of this product algebra on this entangled state can be realized as a linear sum of the action of the algebra of right operators as a direct sum on the original entangled state. And this is not a deep statement, it's just a statement about representation theory. You have a product algebra, you act with it on a state, and you can decompose whatever you get into representations of one of the factors of the algebra. And then once you're given this, on each of these subspaces, you can define this Sj map, and then this S operator is just given by a sum of all of these Sj's, and that's it. And the claim is that that completely generalizes the prescription I presented previously to general entangled systems. Now, what this allows you to do is it allows you to phrase the question of ER equals CPR in a precise setting, and the setting is as follows. So we have some construction now of you know, what the right observer sees as he jumps into the horizon. And now what you can ask is, if you try and act with some unitary on the left, which is some excitation of single trace operators, does the action of this unitary affect the experience of the observer on the right when he is behind the horizon or not? And this becomes a question about correlation functions in the CFT, and by comparing these two sets of correlation functions, you can try and make precise the notion of whether there's a wormhole or not. And there's an equivalent diagnostic which has to do with the commutator of these mirror operators with the simple left operators in your system. So I don't have too much time, but I'll just quickly mention a couple of examples. So you can of course start with the original thermofield double state, which I already described, and you can take these mirror operators as produced by this prescription, and they turn out to have a commutator with the left operators, which is the same as the commutator of the left operators with themselves with their adjoints, and a 2-point function which is also the same up to leading order in 1 by n. And if you compute this and other correlators, you of course find that it's consistent with the original thermofield double geometry. But then you can go to new situations. For example, one of the questions that Marolf and Pulczynski asked in 2013 was, this is very good, but what if you take some generic entangled state where you take the thermofield double and you rotate it with some arbitrary unitary on the left? And if you do this, you can repeat our construction, and you find now that simple operators on the left have a 2-point function that's e to the minus s by 2 with these mirror operators that are defined using this prescription, and they almost exactly commute with these mirror operators. But that's not the end of the story, because if you take a sufficiently complicated operator on the left, you find that the commutator with the mirror operators doesn't vanish. Now, we don't know how to write down a geometry dual to these correlation functions, but roughly the cartoon is that you have a very long wormhole where both the operators on the right and the left see a smooth horizon, and there's a very long wormhole because the operator on the left can do some extremely powerful thing to affect the experience of somebody on the right, but simple operators will not do the job. Okay? But we don't know how to write down a precise geometry. There are other kinds of examples we can consider. For example, one of them is what's called the microcanonical double state, which is obtained by taking just EE states, energy eigenstates, and summing them over some region, and this leads to what's called a low. If you work out the properties of these mirrors and the left operators, it leads to what's called what we would call a low pass wormhole, and that's because you find that for low frequency operators on the left and low frequency mirror operators, the behavior is very much like that of the thermofield double. So it looks like there's a wormhole if you probe the system with low frequency operators on the right and the left. But on the other hand, if you take some high frequency operators, then you find that there's no wormhole, or rather that acting with high frequency operators on the left, you can't really affect the experience of an observer on the right. Now, once again, we don't know how to write down a geometry dual to this, but roughly the cartoon is that you would have some kind of elongated wormhole. Okay, in my last few minutes, let me say a little about the general significance of state dependence. Now, why is it that state dependence is something surprising? So the reason it's something surprising is that if you just had canonical gravity, then canonical gravity would suggest that if you took these relationally defined observables that I described, then you would be able to write them as simple linear operators on the full Hilbert space and not only on this patch of the Hilbert space. However, the limitation to recognize is that this intuition from canonical gravity is not really valid. You can't really get the full Hilbert space of the CFT from canonical gravity, but it is valid for the little Hilbert space, and the analog of that is that the infalling observer can't detect the state dependence within effective field theory, which is what canonical gravity is good for. And something that gets said sometimes is that these operators violate the Born rule, and the translation of that is that if you take these operators that are linear operators in this patch of the Hilbert space and you try and extend them to the full Hilbert space, then these conceptually defined local bulk observables turn into some nonlinear functions on the full Hilbert space, but this is not something that you would see within effective field theory. Okay, in fact, in the eternal black hole, which is an excellent laboratory, you can track down the failure of the canonical gravity intuition very precisely, and the failure of the intuition happens in the inner product in all of these time shifted states. If you take the inner product of this time shifted state with a thermofield double, you find that it has some fall off where the C is the specific heat of the CFT, so you can really compute what this inner product is in the CFT, but this Gaussian fall off actually stops being valid for very large times, and it turns into this ergodic e to the minus s by 2 behavior, and therefore the CFT inner product has a fat tail, this orange curve, which is not seen by canonical gravity. And therefore, this fat tail is what prevents you from writing down a state independent operator. So in this formula I wrote down, it was these cutoffs that were making things state dependent, and if I try to take them to infinity, this is prevented by the fat tail. The formula just doesn't work. Okay, let me just say in the last couple of minutes a little bit about this very recent paradox that's been proposed by Marolf and Pulczynski. So what Marolf and Pulczynski say is that the state dependence can't really work, at least in the single-sided case. So that's where the single-sided, this paradox is phrased in the single-sided setting. And what they say is the following. They say, you say that most states have smooth horizons, so that's what your prediction predicts, that's what your construction predicts. But on the other hand, take your smooth horizon, and just inside the horizon at some late times, we act with some operator that creates a shell that's living just behind the horizon. And because it's living so close to the horizon, the binding energy of the shell with the original black hole cancels off the mass of the shell itself, and the rise in ADM energy is very small, and that's something you can calculate. And therefore, they say that there are as many states with firewalls as there are states without firewalls, and therefore, if your prediction for what's happening in the interior is correct, then these mirror operators are not only state dependent, but in fact they must have a singularity on the Hilbert space. But there's a problem with this construction, and that's because if you try and trace, they added the shell at late times, but if you try and evolve the shell back into the past and ask where it came from, you find that it gets blue shifted, and it undergoes a transplanckian collision with the original matter that formed the shell. And in fact, at this point where it was supposed to bounce off r equal to 0, it doesn't bounce off but forms a black hole at early times. And therefore, gravitational back reaction is something that you would expect would be important for this out of time order correlator that they want to compute. And we don't know how to compute this correlator and how to include this gravitational back reaction, but I would believe that in fact I suspect very strongly that this action of this operator doesn't do what they want, which just leaves the geometry smooth. Okay, so I think I'm almost done. I just want to make one last comment, and that's that we have heard a lot of talks in this conference about entanglement and the relationship between entanglement and geometry, but it's useful to realize that all of these prescriptions are fundamentally state dependent. Now, the moment you write down a formula of the kind area is equal to entanglement entropy, the area is something that's a linear operator in canonical gravity, but the entanglement entropy you can prove is not a linear operator. And very similar comments hold for ER equals CPR, because entanglement is not linear, but the presence of an Einstein-Rosen bridge you might imagine is a linear question in canonical gravity, and the relation between complexity and geometry and other things. Now, this doesn't prove that geometric quantities are state dependent, but it's suggestive, and I think it's useful to keep in mind that the state dependence is something that originates in many other settings, although it's not always recognized as such. Okay, so that's all I have to say. Let me just summarize. I wanted to say that the modern information paradox can be phrased precisely. It is really a question about the existence of certain CFT operators that are dual to bulk fields. This paradox is something that extends also for the eternal black hole, which is a good setting to study this. It can be resolved by means of the state dependent map, and there's some precise map you can write down, and it also leads to a natural setting where you can study the ER equals CPR conjecture. Okay, so that's all I have to say. I'll stop here.
Questions?
Does it work? Hi, Suvrat. So I just wanted to point out that in case of ADS3,
yes,
so it is actually possible to construct
yes,
geometries in the interior, and to do the sort of generalization of the
yes,
Mapplesender-Hartmann entanglement entropy calculation
yes,
by geodesics passing through the wormhole.
Yes.
And make a detailed equivalence between the CFT calculation.
Yes, yes. Sorry, I should have mentioned that Gautam and collaborators did a detailed calculation that went much beyond evolving just with the left Hamiltonian, but in exciting the state in other ways with other non-trivial diffeomorphisms that you have in ADS3, and there you get things where the stress tense actually becomes non-trivial. So what we're doing in general, this left Hamiltonian is a subset of a computation that Gautam and collaborators have done.
Hey, Suvrat.
Hi.
So I guess I just have two comments.
Okay, great.
So first of all, I want to, well, maybe three comments. I'll be fast. So in the context of what I talked about in the previous talk, first of all, that's an example where indeed you have sort of entanglement leading to the emergence of space-time, but there's no violations of the linearity of quantum mechanics. So that's comment number one. Comment number two is that it's true that subspaces.
That's in the absence of black holes.
No, including black holes.
Well,
but so I said, yeah. So let me just make the comments. Comment number two is that it's true that subspaces are relevant for me also. So I agree that in some sense it's the same resolution. Although I think what I was trying to emphasize is how it works. I mean, to describe in more detail how it works. But I should say that you need to explain why it's okay to just restrict to the subspace, right? You don't just get to make it up. I mean, so in our story, there's a physical process that explains why the observables don't need to make sense when you get outside of the code subspace. Okay. Finally, comment number three about the thing you said about the evolving the shell backwards. Actually, the fact that there's a Transplanckian problem is the only reason that your thing has a hope of working at all. Because otherwise we could just construct the bulk operators by evolving them back through the, through the shell, and solving the bulk equations of motion in a linear way. Okay. So what, in this argument of Merrill and Polchinski, it's basically the same argument that I gave a year ago. And it's just using the operators as you want to interpret them, right? So you want to say that the operators are operators behind the horizon, that acting with them creates excitations. And so I think the contradiction really arises within your rules. And within your rules, they're carefully constructed exactly so you don't have to worry about this Transplanckian collision in the past.
So let me just respond to that. So I think the first statement is, I think it's very, the physical justification for why you don't have to go out of the subspace is very similar. It's the fact that when you start writing down correlation functions involving n squared operators, or correlation functions where the energy of one of the modes becomes of order n squared, you don't expect in any sense to expect that these correlators will have a local bulk effective field theory interpretation.
It depends on the correlator.
Well, it depends on, well, I think it's pretty robust. You can do just a, counting and argue that if you have n squared insertions, the 1 over n expansion breaks down. And so I think that's a pretty robust justification for saying, and the only statement we're making is if you have a correlation function with n squared insertions that doesn't have a local, bulk effective field theory interpretation, I think that's reasonable. And also that if you try and insert an energy of order n squared, then that doesn't have an interpretation as well. Secondly, you're right. Of course, if we could evolve things from the past, then there would be no information paradox to start with. So the Trans-Planckian problem, you might say is the reason this construction has a chance of working, but it's also the reason there's a paradox in the first place. So that's okay. And the next comment is that in our construction, I think what we are saying, so certainly our construction needs to be enhanced to take into account this kind of back reaction. So the correlation functions we have written down so far are correlation functions in free field theory, and if back reaction is important, then we need to enhance this correction. But it's something that's computable. In principle, this 4-point correlation function acting with the Marov-Polchinski operator and its effect on the bulk fields is something that can be computed just in bulk effective field theory. So it's in principle a doable computation, and you can fix this construction that we have by adding 1 over n corrections, adding corrections that correspond to this back reaction.
Which you've never said how to do.
Yes, we have not said how to do because we haven't done the computation. That's correct. But I'm just saying, what I want to say, so I anticipated this question a little bit. So let me say the following. You see, the thing is that Marov and Polchinski.
You don't have any more time.
Sorry, yes. let me just answer this question. See, Marov and Polchinski have a prediction for what the effect on the correlators of this phase rotation operator. They say that it creates this particular correlation function. Now, what we are saying is that this operator, so you could have thought the same thing, by the way, in the presence of just evolution with the left Hamiltonian. You might have thought that it creates a phase, but in fact it doesn't. So this is something that you know is wrong, where the intuition from Rindler lets you down. Now this phase operator is more complicated, but you have to note that this naive prediction is just suspect in the presence of back reaction. So they don't have really a good justification for arguing for the presence of this term. And in principle, you can calculate and ask whether that term is e to the I theta omega, or if it's 1. You're right, we don't know what the term is, but I just think that it's suspect without doing this computation.
Okay. Eva.
So I'm trying to understand what you are claiming to have shown. Are you claiming to have shown that the horizon is smooth for a late infaller in string theory on a black hole background? No, so what we are claiming to have shown is that there exists a description in terms of observables that obey effective field theory for a late infaller and in the presence of the eternal black hole. So the way I tried to phrase the paradox was to say that there's an existence question. There's a question of whether you can find these operators at all that will reproduce effective field theory correlation functions. And what we're saying is that you can find these operators provided you're willing to accept the state dependence. Now, there's a question of whether you could ask, are these operators the right operators to use? And our attitude there would be that if you have a description in terms of simple effective field theory degrees of freedom, then that's the description you should use. Now, you could ask, why is that the correct rule? Why can't we have, elephants behind the horizon or something else? And so it's true that we need a more dynamical understanding of why these are the correct operators to use. And that's something that we would like to get from a more dynamical understanding. And also the measurement theory of these operators has to be better understood. But the robust result here is that the existence problem is not there. And given that there is this description in simple effective field theory degrees of freedom, you should use it. And that does suggest that the horizon is smooth for a late infalling observer. Well, I think that was in danger of being in conflict with explicit calculations. But I have another question, which is, you want to preserve unitarity, which is a feature of ordinary quantum mechanics, and yet you're willing to violate the framework of quantum mechanics. Can you say more about why that is? Why are you so comfortable?
I don't think, so as I said, when you say framework of ordinary quantum mechanics, what you're really saying is that you define an observable using words. You say that you look at the area, you jump in from the horizon, you wait for some time, and then you measure something. And canonical gravity does suggest that that's a linear observable. And the reason canonical gravity suggests that that's a linear observable is because if you think of the classical phase space, you can this is a classical function in the phase space which you can lift to an operator in the full quantum theory. But there's no reason really to believe that on the full Hilbert space, some question of this kind, some geometric question of what do you see when you're behind the horizon should be answered by a linear operator. I just don't see. If you ask a nonlinear question, you get a nonlinear answer. So we are saying that the measurement of this process, which is some conceptual observable, is just a nonlinear question to start with. But it is a linear question in an approximation, which is the approximation of canonical gravity in effective field theory. It's important to be consistent with that. But there's no reason to expect from the start that it's a linear question in the full Hilbert space.
So the last question, I think, no weapons. So Douglas.
So this is about this question of the Marov-Polchinski shell we were talking about. I got a little bit confused by what correlator you wanted to calculate, but maybe we could do something simpler where I think I know address this question of back reaction, and if we act with an operator, maybe one of these e to the I n theta type operators, or maybe just a simpler operator at a very late time outside the black hole.
Mm-hmm.
That's going to create that's creating a state kind of like what they wanted to create.
Well, that's right. So that's the correlate.
There I know how to understand the back reaction of this. This is the type of thing Steve Schenker and I have been working on for a while.
Single-sided case?
Yeah. And so what you get is you get a highly boosted quantum right on the you get a shock wave right on the horizon.
In the eternal case, I agree there's a shock wave solution, but in the single-sided case, I just don't understand how that's
right.
the case.
So the way this works is you start up, the right way to understand the back reaction is you start at late time up there where you're acting with the operator up in the top right corner.
So you start off at late time.
That creates a small amount of energy in that frame, but in the frame of the infaller, it's extremely high. So and now we evolve that thing backwards, and it's going to collide with the shell, and make all hell will break loose after that. But we're talking about something that's happening farther up the diagram.
But that's not good enough, actually, because what you need to do is compute this out-of-time ordered correlator.
No, I'm not computing an out-of-time. The point is that you have a shock wave on the horizon, and somebody who falls across it will notice it.
Let me say the following. So you act with this operator, which is this e to the I NW operator, and then I'm going to measure this 2-point function across the horizon to understand what the effect of the shock of this operator is. And now, so the precise computation you have to do in the CFT is this 4-point out-of-time ordered correlator. And it's easy to check that if you just try and compute this 4-point out-of-time ordered correlator in the in formalism, the Feynman diagrams that you have, you need to integrate over virtual particles that reach this place and this place as well. And the invariant distance from this point to this point is actually pretty small because they're almost light-like separated. So it's just not true that you can think about what the operator does at late times and completely forget about the history of the state. Now, that's just not true. It's not true because of what I said. You try and compute this in the in formalism, and you find that you have to integrate over an intermediate point. That the intermediate point can go back in the past.
He's using the out-out formalism.
The out-out formalism has a singularity in the past, so I don't know what you can do with that.
So I think that I know several people had questions, but I think it's a good time to go and have lunch. So let's thank Suvrat.